Welcome to the Mechanics of Solid lecture series. This is a multi-part review of statics with emphasis on the pieces of information that are important for mechanics of materials. Our lesson objective, what I want you to be able to do at the end, is to evaluate external reactions and internal forces in statically determinate structures. The motivation for this is that mechanics of solids is generally concerned with the analysis of stress and deformation in externally loaded bodies. Most problems require analysis of internal force as a first step. To solve for reactions or internal forces, we use the principles of equilibrium, which says that in a properly restrained body, the external loads are in equilibrium or balance with the reactions and the internal forces. Therefore, the reactions or internal forces at any point in the body may be determined by constructing an appropriate diagram, called a free body diagram, and applying equilibrium. The free body diagram may include all or part of the body, and I will give you a couple of examples here. So I've drawn just a general 3D body here with some loads and some supports. If I wanted to solve for the reactions at those supports, I would draw a free body diagram of this whole system. And I would reconstruct the loads acting on the system, F1, F2, and F3, as well as replace these reactions, or replace these supports with external reactions, which I'm going to label R1 and R2. I draw an arrow, a slash through the arrow, which indicates that it's an unknown. Notice that I'm not concerned about the components here. I'm just being very general at the moment. Now suppose instead that I want to solve for the reaction across some internal surface of the body. In that case, I would reconstruct, or I would draw a free body diagram of a part of the body that includes the internal surface that I'm interested in. Like before, I apply the loads over the portion of the body that I'm looking at. So F1 and F2 are of interest. And I will also draw the unknown reaction or the unknown internal force across that surface. And it's a distributed force, so I'm going to draw that with a series of arrows. I'll label it R. Let's have a quick review of the equations of equilibrium. If we're looking at a 2D problem, we have three equations of equilibrium. The sum of the forces in x equal to 0, the sum of the forces in y equal to 0, and the sum of the moments about z at a point equal to 0. For a 3D problem, we have the sum of the forces in each direction equal to 0, and the sum of the moments about x, about y, and about z equal to 0. For the majority of the problems that we're looking at in this class, they're going to be 2D problems, so three applicable equations. A common question is, where should the moment equation be applied? Moments can be summed at any convenient location. However, summing moments at two different locations generally does not provide additional meaningful information. Let's review the support conditions that we're used to looking at. The first one we have here is a pin support. A pin support allows free rotation at the end, so the moment is equal to 0. However, it constrains movement in the x and the y direction, so as a result it can develop a reaction in x and a reaction in y. Pin support generally shown by a triangle. The next one is a roller support, which allows rotation of the end as well as movement in the x direction. So the moment is equal to 0 and the reaction in x is equal to 0 at a roller support. Therefore, the only thing it can develop is a reaction in the y direction. Notice that I commonly show a roller support either as a triangle on wheels or a circle. And lastly, we have a fixed support, such as at the end of a cantilever beam, which constrains all movement and therefore can develop a reaction in the x direction, in the y direction, and it can also develop a moment. Lastly, we review the concept of static determinacy by a series of examples. Which of the following beams is statically determinate? First, we have a cantilever beam. It has, through the fixed support, it has 3 unknown reactions, but 3 equations of equilibrium. So 3 unknowns, 3 equations, we can use those to solve for those 3 reactions. The next one shown here is a propped cantilever. In addition to the fixed support, we have this roller support at the end. Basically, this gives us an extra unknown, so we have 4 unknowns but only 3 equations to work with. This system is indeterminate by 1 degree. However, if we take and we add an internal hinge, such as shown right here, this allows free rotation at that point, and the moment is equal to 0. This basically gives us an extra piece of information to work with, and so in this case we have 4 unknowns but 4 meaningful equations, and this system is statically determinate.